All right, well, part 3 and the last part of our asynchronous lectures. So this will be the last lecture of the semester. So congratulations for getting through your very first semester of college, or at the very least, congratulations on getting through all of Math 16010. So with this, we'll go ahead and conclude our discussion on exponential growth / decay and the entirety of the curriculum for Math 16010. So let's go ahead and finish this up, shall we? So we'll go ahead and recall from last time. The general solution to dy dt equals k times y for k a constant is y of t equals c times e to the kt. Okay? So here, like we said in lesson 35, k being greater than 0 corresponds to exponential growth. Okay? Whereas k being less than 0, as we'll see today, ends up corresponding to exponential decay. Yeah. There we go, that's better. Okay, so to start off, let's go ahead and take a look at an example we sort of saw last time, but we're going to be seeing it in a different light. Because here, the population of a species of fish is decreasing at a rate proportional to the population itself. So if p equals, in this case, 300,000 at time t equals 3 and 250,000 at t equals 5, what's the population when t equals 10? So if you recall from lesson 35 from last time, this whole idea of p is, so recall, so rate of change of p is proportional to p. That's the same thing as saying dp, in this case dt, equals k times p. So in this case, what we end up with is that saying, based off of this recollection up here, p of t ends up equaling some constant c times e to the kt, is what that says. Okay? So here's what's going to happen with this. So like we said a few minutes ago, this example is going to behave very similarly to one of the examples we saw last time. So in this case, what we're going to do is we're going to set up the problem in a similar way. So in this case, if we let t equals 5, then that means that p of 5 has to equal 250,000. Okay? But then when t equals 3, then we should end up with 300,000. Okay? Whereas, so if we focus on this data here, then that's what we get straight from this sentence in the problem statement. But if we focus on p of t as this equation here, we can alternatively get that 250,000 is equal to c times e to the, in this case, 5k, and 300,000 equals c times e to the 3k. Okay? So the thing is that as we saw last time, what we're going to need to do is we're going to need to, in this case, divide equations to get k. Okay? So in this case, we say, all right, well, that means we have to take the ratio of these two things. So we have c times e to the 5k divided by c times e to the 3k. And then we have to set that equal to the ratio between these two numbers. So we have 250,000 over 300,000. Okay? So the thing is that for this left-hand side here, well, as we had last time, well, the c's cancel each other out, no problem. So, and then again, using exponential properties, we should have e to the 2k from this. Okay. The right-hand side, meanwhile, you can either put this into a calculator or do a quick bit of mental math. Either way, you should end up with this fraction here simplifying to 5/6. Okay. So, at this point, we say, all right, now we got to solve for k. So, to do that, you can just take the natural log of both sides, equals natural log of 5/6. And then noting that natural log and exponential inverses of each other, we have 2k equals natural log of 5/6. So, as an exact value, k ends up therefore equaling 1/2 times natural log of 5/6. Okay, so what that tells us is that, all right, so far we get p of t equals c times e to the, in this case, 1/2 times natural log of 5/6 times t. So then if we let, if we plug in t equals one of these values into our function here, we can then figure out what c is. So, as we did last time, just for the sake of picking something, let's let c equal 5. So, in this case, we have c times e to the, in this case, 1/2 times natural log of 5/6 times, in this case, 5. So in this case, we ultimately have 5/2 times natural log of 5/6. So, and as we had up here, p of 5 is equal to 250,000. So at that point, you can pretty quickly see that in this case, c is equal to 250,000 times, in this case, if we divide e over to the other side, then exponential properties should tell us that this is just negative 5/2 times natural log of 5/6. So if you plug this into a calculator, then what you should end up with is that you have approximately 394,360.241. Okay. So as an approximate value, this is what C is. So with problems like this, you want to avoid rounding errors as much as possible. So in this case, you could either, just use the exact value as is, or in this case, you can use the decimal approximation here, but make sure to use all the decimal places given in the calculator to avoid rounding errors. So in this case, like I said, use stored value in calculator to avoid rounding errors. If you want to use decimals here, okay? So in this case, what that says is that if you do end up wanting to use the decimal approximation, that means that P of t, with this reasoning, is 394,360.241 times e to the t times natural log of 5/6 over 2. Okay? And then as a result, P of 10, because ultimately that's what the problem is asking us to do, says, okay, that's 394,360.241 times e to the, well, you let t equal 10, so you have 10 times natural log of 5/6, all that over 2. So that should simplify to 5 times natural log of 5/6. And then, because 10 over 2 is 5, so that's how you get 5 here. And because we're dealing with population, you want to make sure that whatever answer you get as a decimal approximation has to be rounded to the nearest integer. So because of that, you should have 158,485 as your final answer here. And I'll go ahead and say what I had here. So population implies round to nearest integer. Okay? So just all I wanted to say on that. So as I mentioned in the last two lectures, what you'll want to do is, if you want to go ahead and pause the video to catch yourself back up, you can. Or, like I said, if you want to ask questions on the YouTube comments, you can. Just say, at this time, what are you doing here? Okay? But other than that, if you guys want to take a second to pause the video, you can. Otherwise, we'll go ahead and move on. All right? So the next sort of real-world application of exponential decay here I want to focus on focuses more on, radioactive decay and its half-life. So in this case, let's go ahead and take a look at example 2 to see what I mean by this. So we have this radioactive isotope 226Ra, has a half-life of approximately 1,599 years. So if there are currently 15 grams of this isotope right now, how much of it remains after 1,500 years? And we want to round this to 3 decimal places. Okay? So let's do a quick definition of what I mean by this half-life quantity I'm talking about. So half-life, in this context, the quantity, not the video game. Sorry for those that were hoping to see a reference to that, but anyways. So in this case, half-life in this context is the time T naught it takes for only half of original sample to remain. Okay? So that's just the definition. Okay? So here's what I mean by this. So let's take a look at what we're given and what we need to find here. So in this case, we're going to go ahead and use A of t. So we're going to use A again as the amount in this case, sort of like we did last time. So A of t equals A naught times e to the kt. So in this case, like we said, in this case is the amount at time t. A naught is the initial amount. Okay? And in this case, K in this context is going to correspond to our decay constant. So decay constant. Okay? So that's our equation that we're ultimately going to be dealing with here. So what this says is that, right, so A of 0, which ends up equaling A naught in this context, says if there are 15 grams right now, so in this case that's our initial condition, so that's 15, and the half-life is 1,599 years. So what that says is that if we let 1,599 equal t in our amounts function, then we should end up with 15 over 2 at the end of the day. Or, if you want something slightly more general, A naught over 2. So that's what we're given. So we have to figure out, as per the problem statement, how much of it remains after 1,500 years. So ultimately, we got to figure out, well, what is this A of 1,500 value? Rounded to 3 decimal places. Okay? So, let's go ahead and work with that. So, in this case, the problem already gives us the initial amount. So that's just A naught, which is, again, 15. So, you have 15 times e to the kt. No problem. So, now, we got to figure out, what is this k value? So now this is where our second bit of data we have comes into play. So we have A of 1,599 is equal to, well, 15 over 2, like I said. So now, let's just go ahead and let that equal 15 times e to the, let's see, well in this case 15, so k times 1599. So, all we have to do now is just, well, solve for k and figure out what's going on. So what happens from this is that, well, if we divide 15 to both sides, we should have 1/2 equals e to the 1599k. So at this point, if we take natural log of both sides, we end up with natural log of 1/2 equals 1599k. So solving for k, in this case, will give you the exact value. So we have natural log of 1/2 over 1599. So in this case, if you use the decimal approximation here, we get that the decimal approximation in the calculator should be 0.000433488. Okay? So again, if you want to use a decimal approximation here, you can. I won't stop you. But remember, in this case, you have to make sure that you use all the decimals here, or at least as many as the calculator gives you. So again, use stored value. Okay. So as a result, that means a of t is therefore 15 times e to the negative 0.000433488 times t. And then so after that, we say, all right, that gives us our a of t function. So now all we have to do to wrap up the problem is just let t equal 1500, and then we're done. So a of 1500 equals 15 times e to the negative 0.000433488 times 1500. Okay? So at that point, you just go ahead and plug all that stuff into a calculator, and you should end up with, rounded to 3 decimal places, 7.289. Okay? So that's the final answer you should be getting out of this for example 2. Okay? So, give you guys a second to pause the video if you want to catch up. So let's go ahead and move to example 3 for this. So example 3 states, now we have a new radioactive isotope we're considering, 239Pu, has a half-life of approximately 24,100 years. After 1,300 years, there are 4.5 grams of 239Pu, and we're trying to figure out what the initial quantity is. So we've got to round to 3 decimal places with this. So in this case, if we let a of 0 be equal a sub 0 here, if we let that be the initial quantity, okay. So in this case, the problem states that this is what we got to find. Find this. Okay. So that implies we're given that, all right, well, after 24,100 years, so 8 to 24,100. So what that says is that, well, if we start with however much A naught, then that means that the fact that the half-life is 24,100 should tell you that we have that at that point the amount at this time has to be the initial amount over 2. Okay? And then the problem explicitly states after 1,300 years, there are 4.5 grams of our isotope. So A of 1,300 is then 4.5. Okay? So as a result of this, well, again, A of t is still equal to A naught times the KT. So let's go ahead and figure out our constants here. So in this case, if we have, say, if we let t equal, in this case, 24,100, well, we get a of 24,100 equals a naught over 2, which in turn equals, if we plug this into here, a naught times e to the, in this case, 24,100 times k. So now the reason I'm letting t equal 24,100 here is because if you look at this equation here, you'll notice that the initial amount a naught cancel each other out here if we do the algebra. So if we divide a naught to both sides, they cancel out. So we're just left with 1/2 times e to the 24,100 times k. Okay. So then doing the same bit of algebra that we just did back up here, going from here to here, solving for k, you should be able to pretty quickly see that k in this case as an exact value is natural log of 1/2 divided by 24,100. Okay? So as an exact value, decimal approximation, you're going to end up with the following quantity. So you're going to end up with 0.0000286761. So as an exact value, k is this. As a decimal approximation with as many decimals as you need, or given, k is this guy. Okay. So at this point, now we have that. All right. Well, a of t is equal to a naught times e to the negative 0.0000286761 times t. So here we say, all right, well, now we have to use our second piece of data to get a naught from this. So if we let t equal 1300, then we have 4.5 equals a naught times e to the negative 0.0000286761, and then times that by 1300. So what you'll notice here is that the reason why we did not plug a of 1300 back up here was because in this situation, if we just plug it here without knowing, if we plug in a of 1300 back up here without knowing k, we'd still be stuck with two constants, a naught and k. So that's not really we'd be hitting a dead end in that situation. So that's why we had to plug 24,100 into here, and now we've used the amount at 1300 years at this point. Okay? So after that, we say, all right, well, now we go ahead and just solve for a naught from this using exponential properties. So a naught is then 4.5 times e to the, use exponential properties to get that. This is just 0.0000286761 times 1300. So this is approximately, therefore, going to be, if you plug this into a calculator, 4.671, rounded to 3 decimal places. Okay. So this is the initial amount that we started with for our isotope. Okay. So that's example 3. So now let's go ahead and move on to example 4 on this. Okay. So the radioactive isotope 14C has a half-life of approximately 5,715 years. So this problem is being broken up into 2 parts. So a piece of ancient charcoal contains only 78% as much of the radioactive carbon as a piece of modern charcoal. How long ago was the tree burned to make this ancient charcoal? Round to the nearest integer. Okay? So in this case, we have this piece of ancient charcoal that only contains 70% about it as much as a piece of modern charcoal does. So there's definitely been a lot of decay happening. So at this point, if you're trying to figure out, this data of how long ago was the tree burned to make ancient charcoal, well, with problems like this, if you have a percentage of an initial amount, so when finding / working with a percentage of initial amount, a good rule of thumb is to let the initial amount, a of 0, or a naught if you prefer that, let that equal 100. And the reason I'm saying this is because doing that will give you the percentage immediate. So just so that way you don't have to worry about flipping between decimals and percentages in this case, because if you let your initial amount be 100, then you have exactly what you need in both scenarios. Okay? So in this case, we're given that a of 0 is equal to 100, like I said. And so because of that, the half-life, which is 5,715, is then going to end up being, well, that means at this point, that means there's only half of it left, so 50 is our amount there. And a of t is then equal to, well, based off of our initial amount, we have this is 100 times e to the kt. So at that point, that means we have to figure out, all right, how long ago was a tree burned to make the ancient charcoal, which only contains 70% as much as 70% of its original amount. So in this case, we got to figure out, all right, we got to figure out the time t naught so that the amount at that time has to equal 78. Okay? Okay, so in this case, you want to figure out how much time it took to get from 100% of the original amount to 78% of the original amount. Okay? So at this point, that says, all right, well, given our a of t function here, well, the only thing we really got to figure out is, well, what is this k value, our decay constant? So in this case, the only data we haven't used at this point is our half-life data. So we have a of 5,715. That means we have this is equal to 50 because of this. And then if we let t equal 5,715 to this guy, we have 100 times e to the 5,715k. So now we go ahead and solve k as we've been doing. So we end up with, we divide 100 by both sides, we get 1/2 equals e to the 5,715k. So solve for k as we've been doing up until this point, and you should be able to pretty quickly see that k is just natural log of 1/2 over 5,715. So plugging that into a calculator will get you negative 0.000121286 as a approximate value for k. Okay? So as a result of this, well, that means a of t will therefore equal 100 times e to the negative 0.000121286t. So now all we have to do is figure out, all right, now we need to figure out what time gives us 78% of the initial amount. So now you have to solve 100 equal times e to the negative 0.000121286t. Now we have to set that equal to 78. Okay? So divide 100 by both sides, you end up with e to the negative 0.000121286 times t equals, in this case, 0.78. Okay. So then we take the natural log of both sides to get negative 0.000121286 times t equals natural log of 0.78. So then solve for t to get natural log of 0.78 divided by negative 0.000121286 And so that will give you the way to get t from this. So in this case, the problem states round whatever answer we get to the nearest integer. So plugging this into a calculator, round to the nearest integer, we have 2049 is your final answer here. All right. So that's part A. So that was relatively not terribly time consuming, but it definitely had quite a bit of work involved. But thankfully, part B is not so, because we're already given what A of t is as with constants c and k given to us, or in this case a naught. So all we got to figure out now is what percentage of the charcoal remains after 500 years, round to 2 decimal places. So the good news is that because we're working with 100 here as a percentage based off of our initial amount, all we have to do now is just say, all right, well, take this and just let t equal 500. That's all we got to do. So a of 500 equals 100 times e to the negative 0.000121286 times that by 500. So plug that into a calculator, and you should end up with, rounded to 2 decimal places, 94.12. And the good news is that this exactly gives you the percentage you want. So 94.12 is your percentage. Okay? Whoa, that was louder than I thought. Whoops. But the reason I was trying to do that was because, say, all right, that is the last example for lesson 36, and based off of, if you're seeing this in the sequential order of lessons, then this would mean this is the last bit of material for Math 16010. So if this is the last thing you're seeing, it's been a pleasure being able to TA you or teach Calc 1 to you in these interesting times. And I'll have my office hours during the usual class time from 8:30 to 10:30 a.m. I'll see what I can do about some Zoom office hours for finals week, depending on when the window for the last exam is. But other than that, it's been a great semester. Good luck on your final exam, final exams, and have a good winter break, and hope you enjoyed your first semester in college, for those that are freshmen.